Energy conversion is what a power plant is all about. In fact, each unit within a power plant is really nothing more than a factory that takes the chemical energy stored in fuel and, through a series of transformations, converts it into electrical energy. Now, in order to understand and explain how energy conversion takes place, we need a special set of ideas that we call science. Now, science helps us explain and understand how things work and why things happen. Now, science can also clear up some of the misunderstandings we have. For example, you may have heard people refer to a power plant as a place where energy is produced. Well, this isn't exactly true. There's a fundamental scientific principle that states energy cannot be created or destroyed. It can only be transformed. So we really can't say that energy is produced in a power plant. To be accurate, we have to say that energy is converted from one form to another. Now, there are many concepts associated with the processes that take place in a plant, and science is the most accurate way we have for explaining and understanding them. In this unit of the plant science topic, we'll look at energy and energy conversion and the scientific principles that are associated with them. We'll also look at work, power, and efficiency, and how they are related to energy conversion. In other units, we'll cover material properties such as weight and density, fluid flow, pressure, temperature, and heat, all of which have scientific explanations that help us understand how a power plant operates. Energy is a phenomenon that has existed longer than man. Energy is present in all things and occurs in many forms. We can't create it, we can't destroy it, but we use it when we work. In fact, energy can be defined as the ability to do work. One way energy can be used is in a manufacturing process. For example, an automotive factory takes in steel and other raw materials and uses energy to convert them into automobiles according to a particular design. A power plant works in a similar way, except that it manufactures electrical energy. A power plant takes fuel, which contains one form of energy, and converts it into another form, electrical energy. Now, to understand how this process works, we need to know more about energy. We'll begin with the classifications of energy. One way that we have of classifying energy is by the form in which it occurs. Now, there are many forms that energy can take. Now, among those in use in a power plant are chemical energy, thermal energy, mechanical energy, and electrical energy. Now, chemical energy is found in the fuel used in the plant. A good example of thermal energy is the heat in the steam leaving the boiler. Mechanical energy, or energy used to create motion, is contained in the rotation of a turbine rotor. And finally, electrical energy, which is the energy of moving electrons, is the energy released from a generator. Science defines energy as the ability to do work, and we can use this definition as another basis for classifying energy. We'll define work as the movement of an object through a distance. When classifying energy in relation to work, we have two basic categories: kinetic energy and potential energy. Now, kinetic energy is the energy of motion. When something moves, it possesses kinetic energy. Work must be done to produce this kinetic energy. Now, for instance, I'll pick up this book, and I'll raise it above the table. Now, while the book is moving, it has kinetic energy. Now, at the same time, work is done because the book is moved through a distance. Now, basically, any object that is moving has kinetic energy. Now, potential energy, on the other hand, is stored energy, waiting to do work. The book I'm holding up now has potential energy to do work. I can release this energy by letting go of the book and allowing it to fall to the table. Now, the book then performs work because it moves through a distance. Now, there are two words that can help us distinguish between kinetic and potential energy. These two words are moving and stationary. If an object possesses energy and is moving, it has kinetic energy. If it possesses energy and is stationary, it has potential energy. Remember, moving, kinetic energy; stationary, potential energy. Another way of understanding the principles of kinetic and potential energy is to look at how they're expressed mathematically. Now, let's look at some equations for calculating kinetic and potential energy. We'll cover kinetic energy first. The equation for kinetic energy is expressed as kinetic energy, Ke, is equal to velocity squared times weight divided by 2g. G is the acceleration due to gravity. Now, there are two factors that affect kinetic energy: velocity, or speed, and weight. Now, that velocity is a factor shouldn't surprise you, since kinetic energy is defined as the energy possessed by moving objects. Now, later on, we'll find that the greater the velocity, the greater the kinetic energy. Now, the weight of an object is determined by the gravitational forces of the Earth. As with velocity, the greater the weight, the greater the kinetic energy. Now, let's talk some more about the letter G. The gravitational pull of the Earth is a physical constant that causes the velocity of a falling object to increase at a rate of 32 feet per second per second. This rate of increase is represented in the equation by a small letter g. We'll use the equation for calculating the kinetic energy of an activity that takes place in some plants. Now, here you see a forklift moving mill rejects from a pulverizer. The mill rejects and the container therein possess kinetic energy by virtue of their movement. Well, let's say the container and the mill rejects weigh 800 pounds and move at a speed of 8 feet per second. To calculate the kinetic energy of the container of mill rejects, we plug these figures into our formula. Velocity, 8 feet per second, squared, times the weight, 800 pounds, divided by 2 times g, 32 feet per second squared. And simplifying the problem, we get Ke equal to 64 feet squared per second squared times 800 pounds divided by 64 feet per second squared. Now, we can cancel feet and second squared in the denominator with feet and second squared in the numerator. And we're left with feet. Ke is equal to 64 feet times 800 pounds divided by 64. Now, doing the math, we find that the kinetic energy possessed by the container of mill rejects is equal to 800 foot-pounds. Well, notice the units for kinetic energy are foot-pounds. A foot-pound is a unit of energy equal to the force of 1 pound acting through a distance of 1 foot. Well, now that we know the units of kinetic energy and the formula for kinetic energy, let's stop so that you can read the material in the text and answer the questions. And when you come back, we'll look at the effect that a change in velocity or a change in weight has on kinetic energy. And then we'll look at the formula for figuring out potential energy. Now, these principles are not the easiest things to understand, so if you have any questions, clear them up with your instructor before going on. In this unit, our goal is to explain how energy is related to a power plant. So far, you've learned that the units for kinetic energy are foot-pounds. You've also seen how the kinetic energy equation can be applied to the situation of moving mill rejects. And you've learned that when 800 pounds is moved at a speed of 8 feet per second, the kinetic energy possessed by the rejects and their container is 800 foot-pounds. In this segment, we'll use the kinetic energy equation to determine the effect that a change in weight or a change in velocity has on kinetic energy. And then we'll look at potential energy. And we've established that when the container of mill rejects moves at a velocity of 8 feet per second and weighs 800 pounds, it possesses 800 foot-pounds of kinetic energy. Well, let's see what happens if we reduce the weight by 1/2, but keep the speed the same. Plugging these values into the equation, we get kinetic energy, Ke, equal to a velocity of 8 feet per second squared times a weight of 400 pounds divided by 2 times 32 feet per second squared. Now that gives us 400 foot-pounds, which is half as many foot-pounds as there were when the container of mill rejects weighed 800 pounds. So we've determined that when the weight of the container of mill rejects is reduced by half, the number of foot-pounds of kinetic energy that it possesses is also reduced by half. Well, now let's see what happens when we reduce the velocity by half. Now, in this case, Ke is now equal to a velocity of 4 feet per second, squared times the weight of 800 pounds, divided by 2 times 32 feet per second squared. Well, this gives us kinetic energy equal to 200 foot-pounds. That's 1/4 as many foot-pounds as there were when the velocity was 8 feet per second. So, from this example, we've learned that velocity has the greatest effect on kinetic energy. Reducing the weight by half reduced the amount of kinetic energy by a factor of 2, but reducing the velocity by half reduced kinetic energy by a factor of 4. Okay, now let's turn our attention to potential energy. There are many types of potential energy, such as mechanical energy stored in a spring, chemical energy stored in fuel, or the energy that results from the pull of gravity. We'll discuss the principles of potential energy in relation to the pull of gravity. In our examples, the gravitational potential energy possessed by an object is dependent on the position of the object in relation to the center of the Earth. Now, in reality, any object at a distance from the center of the Earth will possess some potential energy. But we'll simplify this for our discussion and consider any object at its starting point as having 0 potential energy. The factors affecting potential energy are height and weight. The mathematical equation is potential energy, Pe, equals height times weight. Well, let's look at an example where potential energy can be demonstrated by using a stack elevator. The potential energy possessed by the elevator at any time during its travel depends on the weight of the load that it's carrying and its position in relation to the bottom of the stack. Well, we can get a better view of the elevator if we look at this graphic. If the elevator is 250 feet high and the elevator's total weight, including the load it carries, is 1,200 pounds, then the potential energy of the elevator would be 250 times 1,200 pounds, for a total of 300,000 foot-pounds. Of course, the elevator doesn't always go to the top, and it doesn't always weigh 1,200 pounds when loaded. Well, let's see what happens when we vary the weight of the load or the height of the elevator in relation to the bottom of the stack. All right, let's say we keep the height of the shaft the same, 250 feet. But we reduce the total weight of the elevator and load to 600 pounds. Now, plugging these values into our formula, we get Pe equal to height, 250 feet, times weight, 600 pounds, and this results in 150,000 foot-pounds. By comparing this to the 300,000 foot-pounds we got before, we can see that by reducing the weight by 1/2, we also reduce the amount of potential energy by half. Well, now let's reduce the height of the elevator in relation to the bottom of the shaft by half, but we'll keep the load the same. This time, Pe is equal to height, 125 feet, times weight, 1,200 pounds, or 150,000 foot-pounds. Once again, we've reduced the potential energy by half. Now, we can then conclude that reducing either the height or weight of an object by half will cause the potential energy of the object to also be reduced by half. Now, situations in the plant where energy is used follow these same laws. Knowing that a specific situation requires a specific amount of energy will help you determine if something is wrong. For example, an electric pump draws a certain amount of current to operate. If the pumping conditions remain constant, but the current drawn by the pump increases, indicating the pump is using more energy, you know that something has affected the energy conversion in the motor or pump. Now, this could signal a problem, and it should be investigated. Well, with this thought, we'll stop so that you can read the material in your text and answer the questions. When we come back, we'll be talking about the conversion of potential energy to kinetic energy. So far, we've looked at the equations for calculating kinetic and potential energy. What we've been doing up to this point is building basic facts that are necessary for understanding what goes on in a plant. In this segment, we'll discuss the energy conversion that takes place in a boiler, turbine, and generator. And then we'll discuss work. Now, first, however, we need to consider a simple example of energy conversion. We'll use this apparatus to help us explain the conversion of potential energy to kinetic energy. Right now, this block is at rest 3 feet above the surface of the table, and it weighs 3 pounds. Now, using the formula for potential energy, PE is equal to height, 3 feet, times weight, 3 pounds. And we calculate the potential energy possessed by the block as 9 foot-pounds. Now, if we set the condition that the block is limited by the boundaries of this apparatus, then we can say that the block, in its highest position, possesses a maximum amount of potential energy of 9 foot-pounds. And when the block is at the bottom of the apparatus, it has 0 potential energy. Now, keep in mind that potential energy we're talking about is a result of gravitational forces. And you know from our earlier discussion that any object above the center of the Earth will contain some potential energy. But we're simplifying our discussion by establishing 0 potential energy at the bottom of the apparatus. Now, this way, we'll only consider the energy we transfer to the block by raising it above the bottom. Now, since the block isn't moving, it possesses 0 kinetic energy. And since the block is at the top of the apparatus, it has 9 foot-pounds of potential energy. Now, if I release the block, it will fall. More importantly, however, it will begin a process of energy conversion, where the potential energy will be changed into kinetic energy. Now we remove our safety pin. Ready? Now, the instant the block began to move, some of the potential energy possessed by the block was transformed into kinetic energy. Now, this graphic will show us what's happening. We've colored the block blue to show it possesses potential energy. Kinetic energy is shown by the color red. The very moment the block moves, some of its potential energy is converted into kinetic energy. As the block continues falling, potential energy, that's the blue, is transformed into kinetic energy, which we're showing in red. Now, this energy conversion continues until impact with the table. Now, at impact, the movement stops, and the kinetic energy is transformed into other forms of energy, such as thermal energy as a result of friction. Some more of the original kinetic energy is transformed into sound energy. The 9 foot-pounds of potential energy originally possessed by the object is first changed into kinetic energy, and then upon impact is transformed into other forms of energy. And we can say, if we remember that the block is limited by the boundaries of the apparatus, that the object now possesses zero potential energy. Now, energy conversion is essential to the operation of the plant. Not only is there the conversion of potential energy to kinetic energy, but there's also the conversion of one form of energy to another. For example, lighting a match causes the chemical energy in the match to be changed into thermal energy. Well, let's look at what all this has to do with the power plant. We'll use this simplified drawing of a power plant to show some of the major energy conversions which transform one form of energy into another until electrical energy is reached. The fuel used in a power plant possesses chemical energy. Now, this chemical energy is released when the fuel is ignited and burned in the boiler. The energy released from the burning fuel is transformed to thermal energy that heats the water and the steam in the boiler. Now, the steam is then sent to the turbine. In the turbine, the thermal energy in the steam is transformed into mechanical energy as it passes through the turbine blades, causing the turbine rotor to turn. Now, since the turbine is connected to the generator, it also turns. The generator transforms the mechanical energy of the rotation into electrical energy that can be used by the plant's customers. Now, we've implied that all the energy in the fuel is transformed in several steps to electrical energy. This is not exactly true because the energy conversions are not 100% efficient. Later on in this unit, we'll be talking about efficiency, and you'll see exactly how much of the original energy that we started with is lost and why. Right now, though, let's begin looking at the reason we caused all of these energy conversions to take place. Work. Now, work is defined as the result of a force moving an object through a distance. In brief, work is what we want energy to do for us. The equation used to figure work is distance times force. Now, there are two factors that affect the amount of work that is done. These factors are the distance that an object is moved and the magnitude of the force. If there isn't any movement, there isn't any work. Well, let's look at an example of work. To raise this 3-pound block 3 feet requires 9 foot-pounds of work. We can prove this by using our equation. Work is equal to 3 feet times 3 pounds. This equals 9 foot-pounds of work. Let's look at another example. In some plants, man lifts are used to travel between elevations. If a 150-pound man needs to ride a lift 30 feet to the place where he's working, how much work must be done to get him there? Let's figure it out. Work is equal to the distance moved, which is 30 feet in this case, times force, the weight of the man, which is 150 pounds. Doing the multiplication, we find that the man lift must do 4,500 foot-pounds of work in order to raise a 150-pound man 30 feet. At first glance, you may have noticed that the equation for potential energy, PE equals distance times weight, and the equation for work, work is equal to distance times force, seem to be similar, especially since we use weight as our force in the work equation. Well, these similarities can be confusing unless you keep in mind what is actually happening with each formula. Work and potential energy are not the same thing. When an object possesses potential energy, it does so because work has been done to it. Let's use this apparatus again to make the point clearer. We said that when this 3-pound block is 3 feet above the table, it possesses 9 foot-pounds of potential energy. Now, in order to move the object into this position, work had to be done. In fact, it took 9 foot-pounds of work to move the object into position. Now, the difference in the formulas is when the movement takes place. While the object is being moved, work is being done. When the object is stationary and waiting to do work, it possesses potential energy. Now just remember, work can only be done when an object is being moved, while potential energy can be possessed even though the object is not moving. Well, we've now seen that potential energy can be changed into kinetic energy, and kinetic energy can be changed into potential energy. We've also seen other ways that energy can be changed from one form into another. For instance, the chemical energy in fuel can be transformed into thermal energy when the fuel is burned. And you've also learned that when an object is moved over a distance, work is performed. Now, this means that it takes kinetic energy to do work. And through work, kinetic energy can be transformed into potential energy. Well, this is a lot of material to think about. So we'll stop here so that you can read the material in the text and answer the questions. When we come back, we'll give you some conversion factors so that you can calculate how much electrical energy is needed to perform mechanical functions. And then we'll look at power. Remember, if you have any questions about energy conversion, ask your instructor to help you. We've calculated the work done by a man lift and the amount of energy released when an object falls. The units that we've used to describe work and energy have been foot-pounds. Foot-pounds are convenient units for our discussion of work and mechanical energy because of the small amount of energy in our examples. However, when discussing the electrical energy output of a very large generator, foot-pounds are too small a unit to use conveniently. When electrical energy is involved, it's more convenient to use the unit watt-hour. A watt-hour is a lot more energy than a foot-pound, but even a watt-hour is too small a unit in many cases. When large amounts of electrical energy are involved, it's common to use units of kilowatt-hours. A kilowatt-hour equals 1,000 watt-hours. In other discussions of energy, BTUs may be used. Now, BTU is larger than a foot-pound, but smaller than a watt-hour. Now, in this segment, we'll show you the conversion factors for converting foot-pounds to kilowatt-hours. And then we'll go on to cover power, the rate at which work is done or energy is used. Now, to begin with, we'll look at the relationship between foot-pounds and kilowatt-hours. 1 foot-pound of energy is equal to approximately 38 millionths of a kilowatt-hour. That can be written as 3.8 times 10 to the minus 5. Now, 1 kilowatt-hour is equal to approximately 2,655,000 foot-pounds, which can be written as 2.655 times 10 to the 6th. Well, to give you an example of why kilowatt-hours are easier to use, let's figure the output in foot-pounds of a generator rated at 10,000 kilowatts. To do this, we multiply 10,000 by the conversion factor, 2.655 times 10 to the 6th. And we get 26,550,000,000 foot-pounds. Well, as you can see, it's a lot easier to talk about 10,000 kilowatt-hours than it is to talk about 26,550,000,000 foot-pounds. And now, in addition to the amount of energy available to do work and the amount of work being done in the plant, we're also interested in the rate at which energy is used or work is done. And when we talk about rate, we're talking about power. Power can be defined in 2 ways, either as the rate at which energy is used or the rate at which work is done. Consequently, there are 2 equations used to calculate power. They are power is equal to energy divided by time, or power is equal to work divided by time. Now, the traditional units for power are foot-pounds per second. but other units that are commonly used include horsepower and kilowatts. Well, now that we have an equation for power, let's figure the power required to move an elevator and its load that together weigh 1,200 pounds, a distance of 250 feet, in a period of 60 seconds. We'll figure it first in units of foot-pounds per second, and then show you how to convert it to horsepower and kilowatts. Now, since we're talking about work done by the elevator, the equation we'll use is power equals work divided by time. Now, work is equal to distance times force, and in this case, the force is weight. So we have 250 feet times 1,200 pounds, and time is equal to 60 seconds. This gives us about 5,000 foot-pounds per second as the power consumed by the elevator while lifting 1,200 pounds, 250 feet in 60 seconds. Now, to convert the 5,000 foot-pounds per second of power into horsepower, we use the conversion factor 1 horsepower, HP, is equal to 550 foot-pounds per second. To do the conversion, we divide 5,000 foot-pounds per second by 550 foot-pounds per second per horsepower, and we get approximately 9.1 horsepower. This is the horsepower needed to move the load and the elevator 250 feet in 60 seconds. Now, to determine the power used to move the load in kilowatts, we can use the conversion factor. 1 kilowatt is equal to 1.34 horsepower. Dividing the 9.1 horsepower by 1.34 horsepower per kilowatt results in 6.8 kilowatts needed to move the elevator and its load over a period of 60 seconds. Since all of the units are interchangeable through conversion factors, it doesn't really matter which ones we use to calculate power. Typically, foot-pounds per second are used when formal evaluations or analysis of systems are made. Horsepower is generally used to rate mechanical components, such as motors and sometimes boilers. Kilowatts are the units used to rate certain kinds of electrical equipment. Well, we'll stop here so that you can read the text and answer the questions. Remember, your instructor is there to help you if you have any problems. In the next segment, we'll be looking at efficiency, and you may be surprised to learn how inefficient a power plant is. One of the primary duties of an operator is to make certain that the plant is operating in the most efficient manner possible. Our purpose in this segment is to teach you what efficiency is. Efficiency is the measure of the amount of energy going into a process compared with the amount of energy coming out of a process. In a power plant, we want to make sure that we're operating equipment in the most efficient way possible so that we produce the required amount of electrical energy while consuming the least amount of fuel. Ideally, we would like to have exactly as much energy coming out as we have energy going in. In other words, we'd like a one-to-one relationship. This would give us an efficiency rate of 100%. But you probably already know that this is not possible because not all of the energy is converted to a useful form, and this results in a loss of energy. We'll use this ball to demonstrate the conversion of energy and energy loss. Now, I'll begin by raising the ball in the air. As I do, I perform work that gives the ball potential energy when it's held in this position. And when I release the ball, the potential energy possessed by the ball is converted into kinetic energy because the ball begins to move. Then the ball hits the table and bounces. Now, if this process is 100% efficient, the ball will bounce back to its original height. Well, as you may have noticed, each time I dropped the ball, it returned to roughly half of its original height. Obviously, the process is not 100% efficient, and some of the energy is lost during the conversion process. Now let's take a look at this graphic sequence to see where the energy goes. When the ball is held in the air, it possesses potential energy. As before, we're using the color blue to indicate potential energy. An instant after the ball is released, the potential energy begins to convert to kinetic energy. We're using red to indicate kinetic energy. As the ball continues to fall, the conversion process from potential to kinetic energy continues until just before impact, all of the potential energy has been converted to kinetic energy. Theoretically, when the ball hits the table, all of the kinetic energy will be transferred back into the ball. And if the process is 100% efficient, the ball will return to its original height. But as you know, this is not the case. At impact, some of the kinetic energy is lost due to friction. More of the kinetic energy is lost as it's converted to sound and vibration. Only part of the kinetic energy is returned to the ball, and therefore it only bounces back to a height related to the amount of energy that is returned. In this case, since the ball bounces back to half of its original height, we can say that roughly 50% of the kinetic energy is returned to the ball. Since only half the energy put in is returned, we can say that the system is only 50% efficient. But not all systems are this simple. To determine the efficiency of any system or process, we use the equation efficiency equals energy out divided by energy in. To determine efficiency rate as a percent, we multiply this equation by 100. The results are percent efficiency equals energy out divided by energy in times 100. Well, let's apply the efficiency equation to the bouncing ball we saw earlier. In order to calculate efficiency, we need to know the energy out and the energy in. The energy in can be determined by the potential energy possessed by the ball before it's dropped. The equation we'll use is energy in equals height times weight. If the ball is held 3 feet in the air and weighs 1 pound, then the potential energy is 3 feet times 1 pound, which equals 3 foot-pounds. This is the amount of energy going into the ball. Well, next, we drop the ball and determine how high it bounces. Well, the height of the bounce is directly related to the amount of energy put back into the ball, which is the energy out. It bounces about 1.5 feet. We can now calculate the energy out by multiplying the distance the ball bounces, 1.5 feet, by the weight of the ball, 1 pound. The result is 1.5 foot-pounds of energy out. We can now plug this figure into the efficiency equation. Energy out equals 1.5 foot-pounds. Energy in equals 3 foot-pounds. Now, dividing 1.5 by 3 equals 0.5. And to get percent efficiency, we multiply 0.5 by 100. And we get 50%. Dropping the ball results in a 50% efficiency. In other words, 50% of the original energy is put back into the ball. Well, what do you think would happen to the ball on the second bounce? Now, we know that only half the energy is returned. Therefore, each bounce will be about 1/2 as high as the last. If you said the ball would bounce 3/4 of a foot, or about 9 inches, you were right. Okay, let's stop here and let you think about what we've said. Read the text and answer the questions. If you have any questions, ask your instructor. He'll help you out. When we return, we'll talk about the efficiency of a typical plant. In the last segment, we figured out how to calculate efficiency. We'll take this a little further and apply efficiency calculations to a typical unit within a power plant. Now keep in mind that we're simply talking about efficiency. You may have heard about a calculation that's done frequently called a heat balance, but don't confuse the two. A heat balance is a much more complicated calculation that will be covered later. Right now, we only want to get across the basic ideas of efficiency. This will give you the foundation to understand what goes on in a heat balance. Now, before we actually calculate efficiency in a typical unit, we must convert the energy in coal and electricity into compatible units. We'll make these units foot-pounds. The average coal used in a power plant has approximately 12,000 British thermal units, BTUs, of energy per pound. To convert BTUs to foot-pounds, you multiply BTUs by 778.3. 778.3 times 12,000 equals 9,339,600 foot-pounds. Next, we'll convert electrical energy expressed as kilowatt-hours into foot-pounds. Now, there are 2,655,000 foot-pounds in a kilowatt-hour. The unit we'll use in our example generates 10,000 kilowatt-hours. This is the amount of energy produced each hour that the generator operates at full load. Well, 10,000 times 2,655,000 equals 26,550,000,000 foot-pounds of energy. We now know the amount of energy in each pound of coal, and we know how much energy is produced each hour of generator operation at full load. If we assume that the unit is 100% efficient, we can make a rough calculation of the amount of fuel that's needed to generate 26,550,000,000 foot-pounds of energy. We do this by dividing the amount of energy produced in the generator, that's 26,550,000,000 foot-pounds, by the amount of energy in a pound of coal, which is 9,339,600 foot-pounds per pound. The foot-pounds cancel, and the result is approximately 2,844 pounds of coal required each hour of full load operation if the unit is 100% efficient. For convenience, we can convert pounds to tons by dividing by 2,000. 2,844 pounds divided by 2,000 equals about 1.4 tons. Now, 1.4 tons would be burned per hour only if all the energy in the coal were converted to electrical energy. But we know this isn't possible. In fact, if we measured the actual coal used in a unit generating 10,000 kilowatts, we would find about 4.2 tons would be burned each hour. The reason for this is efficiency. Well, now that we know the actual amount of fuel burned and the amount of electricity generated, we have the energy in and the energy out. We can now calculate the efficiency of the unit. Efficiency equals energy out divided by energy in. And we know the energy out, that's electrical power generated, which is 26,550,000,000 foot-pounds. To figure the energy in, we must calculate the amount of energy contained in 4.2 tons of coal. Now, first, we need to convert 4.2 tons to pounds by multiplying by 2,000. The answer is 8,400 pounds. Now, we can convert pounds of coal into foot-pounds if we assume our coal contains approximately 12,000 BTUs per pound. The problem would be set up like this. There are 12,000 BTUs in a pound of coal. Now, this would be multiplied by 778.3 foot-pounds in a BTU. And next, we multiply all of this times the amount of coal that is used, 8,400 pounds. Now, the BTUs cancel, the pounds cancel, and when we multiply everything, we end up with 78,453,000,000 foot-pounds of energy going into the boiler. Now we go back to our efficiency equation and put the numbers in. Well, we had the energy out equal to 26,550,000,000 foot-pounds. And we just calculated the energy in as 78,453,000,000 foot-pounds. Dividing the two gives us about 0.33. If we multiply this by 100, we get percentage, which is about 33%. In other words, only about a third of the energy in the coal is actually converted to electrical energy. The rest is lost. We can see why by examining the major components in the steam cycle. We'll consider the efficiency of each component as it affects the efficiency of the steam cycle. First of all, in the boiler, where fuel is burned to produce steam, some of the original energy in the fuel is lost up the stack as thermal energy. Typically, a well-maintained boiler is 85% efficient, which means that 15% of the original energy in the fuel is lost. The next major component in the steam cycle is the turbine. A typical turbine is very efficient, but a lot of energy is lost when steam is condensed in the condenser. Now, this causes the overall efficiency of the turbine to be fairly low, about 40%. So more than half the energy coming from the boiler is lost in the turbine. Most of this loss is due to the heat rejected to the condenser. The generator is one of the most efficient components in the steam cycle. Typically, 98% of the energy it receives is converted to electrical energy. Most of the loss in the generator is due to unwanted heat produced in the generator. Now, in order to find the overall efficiency, you multiply all the efficiencies together. When we multiply the efficiency rate of the boiler times the rate for the turbine times the rate for the generator, we get an efficiency of about 33 1/3%. That's about the same as the example we figured earlier. Nearly 2/3 of the potential energy in the fuel is lost. That's a lot of energy being lost. And if the plant is run inefficiently, even more energy is lost. The way you operate the boilers in your plant has a big impact on efficiency. One example of this is the precision with which you maintain excess oxygen. This is done by adjusting the fuel-air ratio so that there's a little more air than fuel. If you don't pay close attention when you adjust the fuel-air ratio, and you allow excess oxygen to rise as little as 1% above the desired level, a large amount of thermal energy will be carried out the stack along with the excess oxygen. In a typical 190 megawatt plant, this could result in as much as 37 tons of additional coal burned each week of operation. By maintaining your plant in good condition and by operating it properly, you can make the most of the fuel going into the plant. Throughout this unit on energy conversion, we've given you some scientific principles behind how your plant operates in order to supply its customers with electrical energy. You've learned what energy is and how it can be classified. You've also learned the difference between potential energy, kinetic energy, work, and power. And you've seen that at best, a power plant is usually only about 33% efficient. Well, you may not think much about the energy conversion taking place in the power plant because you can't see it. But what you do as an operator drastically affects this energy conversion. What we've done in this unit is establish some groundwork that will serve as a foundation for your learning to actually operate your plant. In future topics, you'll learn more about the specific things you must do to operate the plant in a productive and efficient way. For now, though, we'll stop here and let you read the material in the text and answer the questions.